In this unit, we begin to explore some of the implications or further connections between the calculus of partial derivatives and some of the other properties of surfaces or of applications of those topics. Let's jump right to the examples and see how this would play out. One of the things that we saw in single variable calculus was that we could compose functions, and the same is certainly true with functions of several variables. Now, there's a few different ways we could do this. We're going to study mostly this form down here. If we have a function of two variables, thinking of it as x and y, it's possible that x and y themselves are calculated as a function of time, say, and we'll see an example of this in a moment. It's also possible that those intermediate variables x and y depend on different variables, and what we'd like to be able to do is calculate the rate of change of the final function with respect to the real source variable, in this case here t, in this case here t and s. So again, we just have this nesting of functions, and sometimes we really want to study the relationship between the outermost function and the innermost variables. So the kinds of relationship we're talking about here in the first case is that our time value sets t, assuming it's time, gives us a value for some intermediate variable g, and then g contributes part of the information required to calculate our function f. Meanwhile, the second variable s, maybe something like time or position, maybe, who knows, would allow us to calculate some intermediate variable h, and then the combination of h and g both are required to find a value of our function. It's also possible to have everything really starting at time, and then to have a natural expression of some intermediate values that depend on time, and then the variable we're interested in particular is a combination of those two intermediate variables. And the reason we like to do this, and some students wonder, why can't we just write one big function of time, or write f as a big function of time? And the reason is modularity and simplicity. These might be simple relationships, easy to understand, easy to write down, but the relationship directly between time and the outlying function might be uninterpretable if we wrote it all out at once. But we still want to know, if time changes, how does our function change? So that's going to be what we're studying when we're looking at the composition and the chain rule of multivariate functions. That's all very abstract, vague. Let's jump into an example. We're going to go back to our pressure, volume, and temperature model for ideal gases, and we have that relationship that the pressure times the volume equals number of moles, ideal gas constant times temperature. And we're going to stick with 1 mole for now, just to keep the calculations a little more straightforward. And what we're going to propose is that the pressure is going to be changing at a rate. So notice this is a rate here. And in fact, we can put some formal letters on this. This is the pressure is increasing with respect to time. So just from the variables that we're studying, we know that it's pressure with respect to time. And the temperature is increasing at a rate of 0.15 degrees Kelvin per second. So another rate. Well, that tells us a few things about the relationship between pressure and temperature and time. So we certainly have time dictating something about the temperature and something about the pressure. And again, in an easy, simple form, they're increasing at a nice they're increasing linearly at a nice constant rate. Then the question is, well, what would be the output? What else could we talk about? We could talk about the volume. If we know these, then we can find the volume. But because the pressure and the temperature are changing over time, that means the volume, of course, has to be changing as a result. And how would we know how the volume changes? Well, we'd have to somehow map our way through the relationship of time through the temperature and pressure information that we have, and then out to the volume. So that's what we're going to explore. Making that more formal, we're going to look for dv dt, and again, this is similar to what we saw with functions of one variable. We'll just see how the addition of multiple pathways or multiple input variables changes the calculations.